Hi everybody, Professor Gassimi here. We're on the 6th lecture of the course, and this lecture is going to be covering encoder-decoder models, attention, and transformers. So recall that in the previous lecture, we introduced how you go about modeling text as a sequence. We spoke about HMMs, we spoke about bidirectionality in the context of recurrent neural networks, and we also tried our hands out with a very simple recurrent neural network model on LSTM specifically in the homework assignment. Now, in this lecture, we're going to be extending on some of those concepts to speak about other kinds of network architectures that have performance that's a little bit better than what we've seen with the recurrent structures to date. Specifically, we're going to be speaking about encoder-decoder networks and how we can use an interesting extension of the encoder-decoder network. It's called attention, to create something called a transformer network, which serves as the foundation for all of the contemporary natural language processing tools that you see today. And in our homework assignment, you'll get some experience playing with a little bit of the transformers and looking into each of their specific flavors and implementations. Okay, so to start off, let's think about what we motivated last week's topic with. We were interested in coming up with a method that could perform sequence-to-sequence modeling. And we spoke a lot about the context of classification in the last several lectures, but there's nothing that forces us to perform classification with these networks. We could also use them to do things like language translation, right? So for example, if I had a sentence such as, "The dog ate cheese" in English, and I wanted to translate it to its Spanish equivalent here on the right, I would really love to be able to train a sequence-to-sequence model that can take each of the tokens in the English language sentence and convert it into the appropriate token in Spanish. Well, obviously the way I would start this if I wanted to train such an approach is I would have some data, some training data of some kind in English, and from this training data, I would construct a vocabulary. This is just me sort of reviewing things because later we're going to be speaking about some topics that build on these fundamentals. So I just want to make sure your memory is refreshed. Okay, so we have a vocabulary, and once we have a vocabulary, we can then, for a given sentence, like "the dog ate cheese," we can come up with its one-hot encoded representation. So for example, the word "the" here has a 1 at the position in the vocabulary that corresponds to the word "the," and it's 0 everywhere else. This is what a one-hot coded representation of the word "the" would look like. We can similarly perform this for the word "dog," as you can see, "ate," and "cheese," so that we get the one-hot coded version of the sentence. Now, notice that these vectors are effectively an index of each word's position in the vocabulary. That is to say that this particular one shows up at the 0, 1, 2, 3, 4th location because, cheese is the 4th word in this vocabulary, right? And so one of the things we can do, and in fact that you will see done in a lot of software packages, is to, instead of writing out this one-hot encoded matrix, you just write the index of each of the words in the vocabulary. So 0 means that it's just a shorthand way for me to say that I have a 1 in the 0th location. 2 means I have a 2 in the, I have a 1 in the 2nd location here, or the 2nd index. 5 means I have a 1 in the 5th index location, and so on. Okay, so this is why in some of the software packages, you'll see that they store the index instead of storing the one-hot encoded vector. Okay, but ultimately, once you have these one-hot encoded vectors, let's call them H, you have a matrix of them that represents a sentence. Ultimately, what you do as a first step, as we've seen previously, is you need to turn these into some kind of embedding that's a little bit more meaningful than just the one-hot coded vectors. To be totally clear, you could use these one-hot coded vectors if you wanted. They're not very good representations because they don't provide the contextual value that, let's say, language embedding method like word2vec does, but there's nothing that stops you from using these one-hot encodings as an input to some other model. But as we've discussed, it's pretty much common practice that you'll take these and you do a matrix multiplication with some embedding. These could come from GloVe, as we discussed in the earlier tutorials, or these could be embeddings that you train that represent what each of the vector representations of the words are. And effectively, when you multiply these two matrices, all you're doing is this one hot-coded vector says which index in the embedding matrix you're going to keep so that you get the final consequent representation of your text. So here, the 1 at the 0th index says come here to the 0th column and sort of keep this. The 2 here, the index 2, which corresponds to this second index being a 1, says come here to this and take the second column and place it as the next one, and so on and so forth. Okay. All right, so when we do this, we now have an English text representation, X, okay, for the dog ate cheese. That's why there's 4 columns here. And what we want to do is we want to construct an outcome target. Let's call it Y. And this outcome target could be another one-hot encoded vector for each of the words. So for instance, we could have it so that the outcome for this first word, which was the, is el. And the outcome for the second word is perro, right? And this basically is nice because it gives us this one-to-one mapping between this column that represents the first value of X and this column that represents the outcome that we'd like for that Y. And once you have a mapping like this, you can now train a model to map from the X to the Y. Okay, so one of the models that we had discussed in the previous lecture was the recurrent neural network. And if you think about it, the RNN is a great candidate for this kind of problem, right? Because the RNN at each point in time takes a value of X and it generates a value of Y. So if I have 4 values of X here, I'll be able to have the RNN generate 4 values of Y there. Okay? And recall as well that when we spoke about the RNN, we spoke about 3 matrices. A W matrix that provided some information on the relationships between the inputs, called X1 and X2 here. The value in the parentheses, by the way, here is just referring to which sample. So for example, this is the first sample in X. If we moved over one column, the value inside the parentheses would be a 2. If we moved over one column from there, it would be a 3, and so on. Okay, so this just, the number in the parentheses just tells me which sample we are in within X. Okay, but in either case, regardless of the number of samples, we're interested in taking this input data X and some output data Y, and we're interested in finding some values of W, U, and V that will allow us to map or transform this X into this Y. Okay, now W usually refers in this context to the set of things that characterize the relationship between the input and the hidden state activation. Remember that the stuff in the middle is often referred to as hidden or middle layers. U here refers to how information from the previous hidden state is fed into, in a recurrent sense, when we're trying to generate our output here, which is finally multiplied by V to help us generate the prediction of the outcome variable Y. Okay, so these 3 matrices, you'll sort of see them in a lot of the literature discussed separately. You know, this one is for input, this one's for the previous state, and this one's for mapping from the current hidden state to the output. Okay, well, I also want to make it clear here, because we're going to be using some of these graphical illustrations, I want to remind you that when we put a W1, 2 in this case, along the arrow, what this is really saying is that we take whatever value is in this node and we're going to multiply it by whatever was sitting on that edge. So really what gets passed along here is X11 times W12, and that's what gets passed as an input here. And similarly, also going to that node is, W22, X21, and as well as the recurrent inputs from the previous hidden state. So we were sitting at trying to compute H21, for example. And so we're going to need the value from H20 because that's what the previous hidden state was, right? And from both of these locations. And so finally, when we take all of this together and pass it through the sigmoid function or some other activation function, we get a representation of the next hidden state, so the hidden state value at sequence 1, given the value at the previous point in the sequence, and given the current input. So I have the current value of x is here, as you can see. I have the previous hidden state information that's passed along here, and I use that to compute the current hidden states. And so this equation sort of summarizes what we've seen graphically up here. Now, a more compact way to write this out using matrix algebra notation or linear algebra notation is to simply write the matrix multiplication of U, this matrix up here, with our previous value of the hidden state, plus W, which again relates our inputs, times the current input X as a representation of the next hidden state information. Okay, and we can generalize this so that we say h of t is actually equal to a sigmoid of u times h at t minus 1 plus w times x at t. Okay, so that we have the final equation that defines a vector of the hidden states here that can ultimately be used then when multiplied by v and passed through some other activation function. This could be a sigmoid, for example, or it could be, in the case of this particular problem, it would be a softmax, right? Because a softmax gives a vector of outcomes. We could compute a value for y of t here. Okay, now there's nothing sacred about the sigmoid. I want to make that very clear. We could make our activation functions to be ReLU. We could make them tan h. We could make them whatever we want. So this value of f and g doesn't have to be a sigmoid or a softmax. There are other functions that could be used here. And so the way that people try to characterize how a recurrent neural network works is through these two equations. H of t is g of u of h of t minus 1 plus wx of t. And then finally, y of t is f, some activation function, times v at h of t. Okay, and so these are the two equations that you may see, for example, in our textbook or in the literature. And I wanted to make it very clear how these two equations are derived and how they relate to specifically the recurrent neural network that we discussed previously. Okay, so at this point, it should be clear that we can use an RNN to map from each of the tokens in this input sequence, some value of x, to a vector here that says what the corresponding value of y is. Okay, so for example, if we trained our model correctly, we would hope that v would indicate L as the highest probability outcome at point 1 in the sequence. Pero would be the highest probability outcome at point 2. 8 would correspond to comillo, and cheese would correspond to queso, and we would be good to go. Now, this works well because we have a one-to-one correspondence between each of the English words and each of the Spanish words. But what if we wanted to go from English to another language like French, where there's no longer a one-to-one correspondence between the tokens? You can see that the 4 tokens here now become 6 tokens here. So the point of today's lecture and the underlying motivation for what we'll be discussing in the rest of the lecture is models that can help us more generally overcome this kind of problem. That is, models that are more general sequence-to-sequence paradigms.